God, looking scruffy without my hat on. All this mad professor stuff driving me crazy. It might be a practice, let's see. So time particle theory, this is Eulers Axis theorem. I've got my glasses on, so I'm serious. Let's have a look. That helps. So this is Eulers Axis theorem. Yeah. In 3D space, any displacement of a rigid body such that a point remains fixed equals a single rotation about some axis through the fixed point. So what it means is that through the center point of any, let's go over there, through the center point of any system, there will be a rotation, a full rotation, if any point of that sphere moves at all. Now, this is where we can take it into time particle theory, the waves, because it moves it into 4-dimensional, and in fact it becomes 5-dimensional analysis. Because instead of it, you're assuming a rigid body, yes, it's rigid, but it's absolutely elastic. It's elastic membrane theory, remember, that's Leve, that's what he's talking about. So all this is Leve, of course. Elastic membrane theory. And it means that the rotation inside must be fluid and it must be infinite. So there can be no restriction on this motion. Because what it's saying is that I'm going to take my time particle, and if I try and move it at all, any motion at all that I try and put into that, I'm trying to twist it this way, let's say, will result in a rotation in the middle. So it would have a mass resistance, if you like. It's like imagine a clockwork machine. It goes, as I push it, it would go zzz, as it was inside. That's the concept. So just quick recap on Leve, of course, wave cases. And here is the fluid motion describing inside. And of course, I've taken my favorite doc, the one he gave me, AB5, and I've used that as my load case, the fourth load case. This one, and I placed it here. And this just represents one stage of the motion of the wave, which is all of those ones. Okay. So what happens to with Euler and his this is a time dependency factor here that we're going to end up with. So we'll start over here with I, the imaginary number, the meter 4. The motion of that I is around the outside. The easiest way for this rotation to begin to occur, if I was going to try to move this, remember, let's say I'm going to try to move it this way, rotating around its north-south axis. Okay, so I'm going to try and twist it this way. That makes more sense, I think. As I try and twist it that way, the second moment of area moves around the outside until it gets to a point opposite where it started from. Now, because it got there under its own steam, I'm just trying to twist this, and I've put in an infinitesimal displacement, the symbol delta, which is all about the matrix calculus. You use that matrix calculus to solve that delta. So I've given it a tiny motion. This is kicked off. The second moment of area has done the easy route around the outside, doing a 2 pi. This is pi, 2 pi, but half the circumference. And when it gets to this point, it has created something. It's created a space in time within this duration, and it returns. It just returns back. You get what's called total internal reflection of the light, TIR. It's a theory. There's a lot about it. It includes the critical angle we'll come to. So the light is reflected back inside, doing this motion over the top. The arrow of time, the movement of this thing on the x-axis in time in real seconds, means that this point is now at the center. And so it has moved. It does that reaction. And as a reaction to that, it moves this way, inside, aiming for the center now. It's trying to get this rotation into the center. So the force I put in has moved to the center via this action there, and then there's an opposite reaction to it at this point here. Now there's such a thing, this is my particles, remember now? So I've got my alpha particle, and I've shown that on the outside, and my beta particle, and I've shown that on the inside. The outer particle is bigger because it's based on the golden ratio pi. And I saw a lovely video by this guy, Jane Academy, check him out. So he's got all the background for that. He'll explain how he constructs this symbol, and it means the golden ratio pi. It's based on root 5. Go and check him out. And the answer is 3.144, and it's a bit more repeating, but look, it's bigger than our standard pi. So we end up with two circles, a golden ratio pi circle and a static one that we observe when we draw a circle pi, the 3.14159, the 3D. Okay, and it represents potential energy. But here is the kicker for this. The reason that the golden ratio is so beautiful is because it represents motion statically. So it looks good to us because it's motion captured. Can you understand that? The motion that we see of this energy, I've split it out. It moves around the circumference, it goes over the top. And here's the equal and opposite reaction. Now, the outer one is based on the golden ratio, because that builds all the Fibonacci stuff is built from that motion, angular momentum. It's twisting. It puts one twist in when it goes through that motion. I tried to show that there. And then when it goes, it twists again. So that's where you get the 720 twists. 1, 2. When you end back at the center, when you're measuring stuff, you're seeing a 720 twist in everything. But it means that you don't meet in the middle. Because this is the 3.144 pi, and this is the 3.14159 pi, there's a gap in the middle. Don't meet. But they do meet, because there's a reaction, a spark. It creates the zero. That's how the zero energy is actually created right here in the center of all the action. And it's this energy that creates this motion in the first place. It's self-replicating, and it's the relationship here between the gap. It's the spark gap. Spark gap of the spark plug is here. The points are somewhere else. I found them. Dwell angle. So let's have a quick go through how this axis is created. So what I'm going to show you is you've got a y-axis, an x-axis, and a z-axis runs through this. The three axes of the one at the beginning I stole from Wikipedia, which shows the three axes. And then there's also a vector axis, which has a rotation and it has a vector that's different from the other three. And in this case, it's created from the critical angle. Now, this is the bubble bursting. I'll just go through these again. These two, when at the end of a cycle, it looks like this, and that should pop. Those two waves crash into each other, that would burst. But before it bursts, it goes through this motion as it tries to burst, yeah, and it doesn't burst, it creates that. So you end up with jumping from this to this every time. And here's that low case 4. The bubble in this case is here, and it's going like this through the motion. So this angle, right, because that is spinning, it is not spinning flat. It generates a bit of lift here, because this is a vacuum gets created, and this is a pressure, and so you get lift generated there, and that lifts the equatorial axis, giving you the critical angle, and guess what it is? It's 137 arc seconds. Surprise, surprise. Creating the vector axis, and this is why our north axis and our true axis, true north, don't line up, and why they're so unstable in some ways, because it's the final. Look how finely balanced they are. It's Eulers Axis theorem. So the greatest mass moment is created not here. It's created there. That is the greatest mass moment, and that is a conscious mass moment. It is our life being created. The light that we are and that we generate is created in the system there. Proven by Levy in 1915, proving Eulers Axis theorem 1775. I think we've waited long enough. I'd like to get started on this experiment and get the planet set ready for the future. I'd like to start right now, but I can't do it alone. I've got to wait for you. All I can do is put videos down, and hopefully they'll make some sense to somebody, and eventually you'll go, we should look at this. Welcome to New Earth.